Charts and maps are one of the most important ways that a geologist, an oceanographer, a meteorologist gets their information out to other scientists and then to the general public. So map reading and cartography, charts generally is the term used for oceans, and maps is generally the term used for land, is the topic of today's lesson. We describe the location on Earth by using a grid system. We've all heard of latitude and longitude. Picture it the same way you would an XY graph, where you chart the points and give an ordered pair. Usually in math it's X comma Y coordinates, and in the Earth it's latitude comma longitude coordinates. They are not in normal numbers, they're in degrees. So you would give the degrees north or south for latitude. Please put N or S, and then east or west for longitude. So latitudes measure the angular distance from the equator, which is the 0. The important lines of latitude are the equator, 0, the tropics, the Arctic, Antarctic Circle, and the poles. The poles are 90. Now the Earth is tilted on its axis, which leads the tropics and the Arctic and Antarctic Circle, because above the Arctic or Antarctic Circle, the sun can stay set for 24 hours. In the tropics, you get a day, actually 2 days, where the sun is at the zenith at noon, 90 degrees. So those are not arbitrary lines. They're solar lines based on Earth's axial tilt. The axial tilt is also called the obliquity. The longitude are lines analogous to the y-axis. The 0 was agreed upon internationally to go through Greenwich, England. That is called the prime meridian. The international date line is 180. It's on the other side of the world. The Earth spins at 15 degrees per hour. So every 15 degrees you have a time zone. So there's the prime meridian dividing the eastern and western hemisphere. Greenwich, it's called the Greenwich meridian, and Greenwich time is the zero, and then everything is measured from Greenwich time. 15 degrees would be an hour. Latitude is always written first, and you always include north or south. Longitude is always written next, and you always include east or west. Here are some examples of how to find latitude and longitude. You see point A. What are the coordinates of point A? 60 degrees north, that's first. You look at the 60 degrees on the left-hand side. The numbers are very small, but that is a 60. And 30 degrees west of the prime meridian. The blue lines show you where the equator and the prime meridian are. So B is in the southern hemisphere, 15 degrees south, still in the west, 105 degrees west. C, down in Antarctica, in the eastern hemisphere here, 75 degrees and 75 degrees south. And of course, D in the middle of our United States. Polaris, the North Star, an average star. It's not overly bright. A lot of people think that it's a bright star, but that is the star that is located almost directly over our North Pole, and it appears to stay stationary in the evening where other stars go around it. That is the star that was used by ancient explorers to navigate because it stays stationary, and it is north. Wherever you are, the distance above the horizon for the North Star is your latitude. Please remember, in the southern hemisphere, you don't have the North Star. The UTM grid coordinate system is used by surveyors and military. We will see them on the side of some charts or maps, but we will disregard them because that is out of the sphere of our course. So we'll look at topographic maps. Topographic maps show the features of Earth's surface. Topography then is the Earth's surface features. They record the change in elevation by lines, giving a two-dimensional map a three-dimensional quality. And then ocean floors have what we call bathymetric maps, which are basically topographic maps of the ocean floor. So this is a typical USGS segment of a topographic map. You can see the streams going through it, and the lines are far apart in the stream. That is indicative of flat. See the hills on either side of the stream. The lines are close together. That is indicative of steep slope. The closer the lines are together, the steeper the slope. Now, water flows downhill. So when you look at the elevations, you know that the water is flowing downhill. It generally flows into V's if the lines cross the river. You can see every so often, in this case 100 feet, you have a darker reference line and then the contour lines in between. And then the highest point of Caddy Hill is given an exact elevation. If you're given a point between lines, then you have to estimate. In the upper right-hand corner of most topographic maps, you get the title. It's called a quadrangle because it has 4 angles. You're giving the state. 7.5 minutes refers to a degree is divided into 60 minutes. And 60 minutes is divided into 60 seconds. So a 7.5 minute series is 7 minutes 30 seconds. In the extreme corners, you'll see the latitude and longitude. This Arizona is 35 degrees, 22 minutes, 30 seconds north, and 111 degrees, 30 minutes west. The other corner would be 7.5 minutes different. The UTMs, as you can see, are listed as well, and we are going to disregard them. On to some topographic maps. Topographic maps, then, you can see in this three-dimensional image, map the surface, the elevation changes of landforms. It's a two-dimensional model representing a three-dimensional world. They're known as contour maps. And they show elevation from sea level up to the highest mountain peak. The bottom of them have a scale where you can make a little makeshift ruler and measure distance. The 1 to 24,000 means that head has been shrunk 24,000 times. And the contour interval of 40 feet is 40 feet change in elevation between lines. So those are contour lines. They show change of elevation. Any place on that same line is equal. They can be used to show the shape of the landforms. We call the difference relief. In math, it's called slope. That's the change in elevation. The contour interval is the distance or change in elevation between two lines. You can see here the contour interval is 20. Every fifth line is darker. That is called the index contour. Index contours have labeled elevation. Contour lines generally form closed loops. Most of the time they run off the side of the map, but they form closed loops depicting mountains and valleys. You can see here the streams flow into the V's from a higher elevation to a lower elevation. That dotted line is called the watershed, so there all the water flows to the stream. Outside of there it flows elsewhere. That's called a watershed. And the river flows into the V's, in this case, south. V's always point up the hill. So the maximum elevation is 1 foot less than the next contour line would be. Sometimes you have to estimate then. Rarely you're giving the highest contour on the map, but most of the time it will take an estimation when you list the highest or lowest elevations, except when there's the ocean, the lowest would be sea level. Depressions are shown as well. They have dashed lines called hatchers to show a depression. Benchmarks give you the exact elevation. We talked about that on the map. They have a little X and then the exact elevation. There's a benchmark on a map. Gradient or relief is the slope of the land. You measure the distance, take the elevation change, divide it by that distance, and you're giving a slope, usually in feet per miles. North Pole's always shifting. In a map, you're giving geographic north, that's 90 degrees. Polaris, we talked about that a little earlier, and magnetic north to where your compass points. Magnetic north is not centered on geographic north, so your compass heading will change depending on where you are on the planet. So here's some topographic profiles. The contour map shows you the 3 peaks and the elevation changes. Like I said, bathymetric maps study the ocean floor. Isobaths are analogous to the contour lines, and they're read in much the same way, except it's depth and not elevation. Here's a bathymetric map of the Gulf. You can see off the coast, it is relatively shallow, gentle slope. Then you have a steep drop off called the continental slope, and then the abyss again is deeper and gentle. These are taken by soundings. In the early days, they were taken by plumb bobbing. Now they're used soundings, or even satellites can measure the minute changes of the surface of the ocean and chart the seafloor from that. So on a nautical chart, a lot of information is put there, like rise and fall of tides, day markers, water depths, configurations of the sea bottom, reefs and other dangers, magnetism, and the nature and form of the coastline. The United States claims 12 nautical miles as its territory. Then 200 nautical miles is exclusive economic zone, which means all the minerals or resources found in that 200 nautical mile distance belongs to the United States or whatever nation you're looking at, but the sea itself is international waters. So in 1982, the International Law of the Sea was adopted for this. A nautical mile is based on latitude, where a statute mile is far more random. Nautical miles are a little bit longer than statute miles. The compass rose then shows you the difference from magnetic north to geologic north and Polaris on a map or chart, and you can use that to plot your headings. All of this was made a lot easier with the advent of onboard GPS and chart plotters.